Physical sciences deal with non-living things. And so in chemistry, we're dealing with the study of non-living things. Okay, so chemistry is considered a physical science. Biological sciences focus on living things. So throw out some examples of physical sciences. What are some other examples of physical sciences? Just throw them out.
Sig figs.
What'd you say?
Sig figs.
Okay, no, of like branches of science. Like what are other classes you could take that are physical sciences? Okay, is it living or non-living?
Wait, physics?
Physics is a good one. It's a physical science, I would agree. What else? What are other science classes you could take? Not here necessarily, but in general, right? What are other categories of science that are physical sciences?
Chemistry.
Yes, chemistry, physics, what else? What else?
Is it obvious?
It feels obvious, but...
Physical science.
Okay, yes. That would count, yes. I'm thinking of astronomy, astrology, geology, right? All of those categories, maybe not super obvious, but all of those categories deal with non-living things. Tell me some biological sciences.
Biology.
Yes, very good. Botany, good. What else? Anatomy, yes, all good.
Psychology.
Yes, I think that falls into a social science, I think, but okay. Any other ones? Dealing with animals? Zoology. Yeah, zoology. Yep. All right, very good. Paleontology, I think, would fall into a physical science, right?
Why do you have superhuman hearing?
I have everything.
Miss Noll's just perfect, guys.
Oh, yeah. No. Okay, I want to read through the definition here of chemistry, and this is not something that you'll need to memorize. Memorizing things is not my style, so you will not have to memorize definitions really ever, but I want to break the definition down a little bit. I hardly ever have you write down full definitions, but this one I do want you to write it down. So I'll give you a couple minutes to get it written down, and then we're going to break it up and kind of walk through it. Is a molecule. Have we heard these terms before?
Yes.
Okay, good. So atoms are the smallest part of an element that is still that element. I took the book definition and changed it a little bit, but it's the smallest part of an element that is still that element. Okay. Because what do we know that makes up an atom? What are the three things that make up atoms?
Neutrons, electrons.
Yes. Protons, neutrons, electrons. They make up atoms. And so when we say the smallest part of an element, well, the smallest part of an element might actually be the electron. But an electron on its own has no properties, right? It just is the electron. But a certain arrangement of protons, neutrons, electrons makes an element, right? It has to have a certain number of protons, neutrons, electrons. Take a look at this periodic table real quick. Okay, can we find oxygen? Where's oxygen?
Top right.
Top right, number 8. Do you know what the 8 represents? How many protons? Very good. So oxygen has to have 8 protons. It has to. If it doesn't have 8 protons, it's no longer oxygen. Right? It just isn't. That's its single identifying characteristic is the number of protons. Because the number of neutrons can change and the number of electrons can change. But protons cannot. So if we're talking about an oxygen atom, if it no longer contains 8 protons, it's not oxygen anymore. Okay, so an atom has to contain certain characteristics or certain arrangement of protons, neutrons, electrons to be an element. A molecule is 2 or more atoms that are chemically bonded. Okay, chemically bonded and acting as a unit. So can you tell me what does it take to make a chemical bond? Any ideas?
A nucleus.
Okay, nucleus are involved, electrons are involved, good. What has to happen with the electrons?
Is more than...
They go together.
They go together, yes. Have we heard about ionic bonds or covalent bonds? Do those ring bells?
Yeah.
Okay. So in order for an atom to be chemically bonded to another, there has to be an electron transfer. An electron transfer or an electron sharing. right? Covalent bond is sharing of electrons. Ionic bond is trading of electrons. And so in order for things to be chemically bonded, there must be some sort of electron exchange, if you will, right? Whether it's in terms of sharing or that. Otherwise, they're just two atoms hanging out next to each other, right? Chemically bonded now makes it a molecule, okay? So tell me here, is there a difference between these two things? Is there a difference between this and this?
Yes.
What's the difference?
Okay.
Yeah, go ahead, Paul.
The first one is just two hydrogen atoms just sitting next to each other, while the second one is they're bonded together.
Bingo, right? So this right here, do we know what this is called?
Exponent.
No.
Oh, subscript?
Subscript, good, a subscript, because it's on the bottom. Sub means below, so subscript here. And then what's this called? What's this guy? Think about algebra. What's a number in front of a variable called? Coefficient. Yeah, a coefficient. Coefficient. Okay, so the coefficient in front tells us how many of those molecules there are, and the subscript tells us how many of that particular atom there are. Okay, we'll talk a lot more about this as we work through it, but that's a good introduction. We need to understand there is a difference between these two things, right? This one is just two individual hydrogens, and that one is two hydrogens that are chemically bonded. So now that becomes a molecule. Okay? All right, very good. All right, I just talked about that. When subscripts, we use subscripts when there's more than one atom in a molecule. So, all right, good. We feel good about that? I just said it. I was getting ahead of myself. Okay. A chemical reaction happens when one substance changes to another by reorganizing the way atoms are attached to one another. Okay, so here down here we have like a spatial representation of a chemical reaction. There are two water molecules on the left. Do you see that? The oxygen is red. The little white ones are hydrogen. It splits it apart and now it becomes an oxygen molecule and two hydrogen molecules. So this is a chemical reaction. Do we know what the things on the left side of a chemical reaction are called? So let me write this out in terms of the actual chemical reaction. We have 2 H2O, and now it becomes 2H2 plus O2. Okay, that's a chemical reaction. Have we seen those before?
Yeah.
Okay, what are the things right here on the left called? Almost. The reactants. Very good. Okay, so these are called the reactants. And the things to the right of the arrow are called, it's what the reactants produce, so they are called products. Okay, they are called products. Okay, so anything on the left of that arrow considered reactants, anything on the right of the arrow, it's considered products. And so this arrow represents like yields or produces, right? We're saying these two things are going to mix together, or in this case, one reactant splits apart and forms two separate products. Okay. How familiar are we with chemical reactions? Have we done like balancing of chemical reactions?
A little bit in grade.
A little bit in 8th grade. Okay, perfect. Physical science, some of you guys did that with me, I think, but it's been a while. Okay. All right. We're gonna. I don't want to go through the scientific method a lot. Okay, so we're gonna breeze over this because you guys have heard the scientific method how many times? Like 6 years in a row, probably. So I'm not gonna spend time on this. But this is the overall theory, right? There's all sorts of ways to write the scientific method, all sorts of graphics and whatever it is, right? But it starts with some sort of experiment, right? We make an observation, we make a hypothesis, we do the experiment. We do all of these things. But then what happens after that experiment is done is we have to put our results into some category, right? Our results either become a theory, a law, or a model, right? And so we can have lots of different things that happen to our results. This one tells me that if there's a theory that has to be changed, we can make a prediction on it and then go back through the experiment process. But all of this has to happen based on a question being asked, right? There's got to be some inquiry that causes us to go into this method of scientific experimentation. We have to have some sort of question that jumpstarts it. One more thing here. We said your results can become a theory or a law. Do you know the difference between those two things?
One is like an idea and the other is like a fact.
Okay, almost. Very good. A law, we call scientific laws, but do we 1000% know they're true? No, because we can't. But what we can know is that they have yet to be disproven, right? So we pretty much call gravity a law, right? Because we've never seen it not work. But do we have the ability to know that absolute truth? Not really, but we have yet to disprove that thing. So that's considered scientific law, right? If we go years and years of experimentation without disproving them, we consider it a law. Theory means that we have a pretty good idea, right? We think this is what's happening, but there's still options for, or I guess opportunities for that to change. A lot of what we know about the atom is still named theory, right? It's still named atomic theory because we're still learning things about the atom itself. But, okay, very good. All right, I'm gonna. When we take observations and when we do the scientific method, there are two categories for taking observations or taking data. I'll let you write these things down and then we'll kind of go from there, but I'll give you a second to get it. 4, qualitative and quantitative. Mm-hmm. Qualitative means they are physical qualities that we can typically observe. And quantitative, what's that prefix quant mean? Number, right? So quantitative data just means we're putting a number to that observation. So we want to have a quantity that goes with it. So when you're doing observations or when you're collecting data, you can collect both quantitative and qualitative data, right? When I say it's bubbling, is that qualitative or quantitative? Quantitative or qualitative. And then when I say it bubbles at 100.4 degrees, that's quantitative, right? So you can take all of those types of data when you're doing that. But quantitative data involves a measured number, and that's really what we're going to deal with the most, okay? I'm going to skip over the scientific models because we kind of already talked about what that looks like. So we're going to go into our quantitative measurements. Our quantitative data has to have two parts. It has to have what's called the magnitude or the number, and it has to have a unit, okay? Give me some units that you're familiar with in terms of metric system units, because that's what we're going to use here. Kilogram, millimeters, milligrams, good. What else? Kilometers, centimeters, all good. What about a volume unit? Liters, good. We've done grams, meters, liters. What about a time? What's the time unit? Is there a difference?
Seconds.
Yeah, there's no difference between metric system and hour system time, but seconds is your metric system. They don't keep time differently over there. No, these are some units that we're gonna start dealing with. If you had to rank yourself about how comfortable you are with the metric system and using the prefixes, where would you put yourself? 5 or 1 to 5? Where would you say? Metric system? Decent? Okay. All right, good. We're gonna review that too as well. Okay. These are just examples of measurements. There's your number. There's your gram. There's your number. There's your unit.
Okay. Is it Kelvin? Which one is that? Is it
Kelvin is temperature. Yep. So in science, we use either Celsius or Kelvin, just never Fahrenheit.
Kelvin?
Kelvin is just, it's a scale that starts at 0. So there's no negative Kelvin.
Doesn't it measure like the 0? Like it's so hot and it's so cold. Something like that, like 0 cold.
What's it called if we reach 0 Kelvin? More than freezing.
Dead temperature? I don't remember it.
Absolute 0.
Oh,
It's called
yeah,
absolute 0. Yep. If we were to reach a temperature so cold that we reach 0 Kelvin, then we would reach what's called absolute 0. And at that point, all energy cease to exist, right? Or cease to do anything. So that would be a problem for us, right? Yeah, it wouldn't be good. For instance, 0 degrees Celsius, that's freezing temperature of water, right? Is 273 Kelvin. So absolute zero would be negative 273 degrees Celsius. So it'd be pretty cold. What's up? Oh, okay. All right, here are what we consider the base units or the fundamental units for the metric system. Did I print this chart for you, or do you have to fill it in?
We just have to fill in the abbreviation.
Just a couple of them? Oh, the abbreviation. I'm sorry.
The oxygen molecule one, which is an empty box. I think you skipped over it. Yeah.
Oh, okay. Okay, how many of these are familiar to you? Have you heard of kilograms?
Yes.
Meters?
Yes.
Seconds?
Yes.
Kelvin?
Yeah.
Amperes?
No.
Okay, what about amps?
Yes.
Same thing.
Okay.
Same thing. Moles?
No.
Yes and no. Some of you yes, some of you no. Oh, we're going to get very familiar with moles in here. Very familiar. And then candelas. Have you heard of candelas? You might see those on like light bulbs, right? It's like how it measures how bright something is. Luminous intensity, okay, is measured in candelas. Ones that we will use in here, those three really are the ones we'll use the most. Physics will use this guy, this guy, maybe that guy every once in a while. Okay. Oh, that. So in chemistry, that's where we use, those are the ones you use the most. Does one of them stick out to you as different than the others? What does it stick out to you as different? The question I asked myself, well, why isn't the unit just gram? Right? Why isn't the fundamental unit just gram? Why is it kilogram? Do you have any thoughts on that? What'd you say?
The grams are super small.
Yeah, grams are super tiny. So if we measured everything in grams, like day-to-day life, if we measured everything in grams, everything would be in the thousands, right? So instead of saying something weighs 1.2 kilograms, I would have to say it weighs 1,200 and something grams, right? It just makes our numbers a little bit more manageable. So that's the only one that I think is a little bit different. So, yeah, okay. This is a unit chart for the metric system. And I made this chart because this is the way that my brain thinks. I don't want to have to deal with fractions or with small decimals. So what I did with this chart is I made the larger unit always get a 1, right? I'm going to say how many of the smaller unit are contained in the larger unit. Does that make sense? Instead of saying a meter is 1/1000th of a kilometer, I'm going to say a kilometer is equal to 1,000 meters. Does that make more sense?
Yeah.
Okay, so that's how I have the chart laid out. The larger unit always gets the 1. So in this one, you see how each of them I only put a U there for unit, but it applies to every single one. So I could say 1 kilogram is equal to 1,000 grams, right? I can trade that U for whatever unit I need to use. Grams, meters, liters, seconds, whatever it is. Does that kind of, are we on the same page with that? Okay. So if I were going to ask you how many millimeters were in a meter, what would you tell me? 1,000, right? How many millimeters are in a meter? You would tell me 1,000. Okay. For some reason, our exponents didn't copy over very well here, so this should be 10 to the 6th and 10 to the 9th. Okay, so
Yeah.
they did it on yours, fine? Okay, perfect. Have we seen this little guy before?
Yes.
Okay, do you know what that Greek letter is? Or what it stands for?
What is it?
I don't care about the Greek letter itself. This right here,
Forget.
this stands for micro, and it's a Greek letter. I write it just like as a little U with a tail on the front. Okay, so that's how you'll see me write that for micro. That's like a million tiny things in the base. Okay? Do we feel comfortable with that chart? 1 milliliter is equal to 1 centimeter cubed. That's what type of a conversion? What does milliliters and cubic centimeters represent? Does it represent distance, time? What do you think? Volume. It's a volume. Okay, because centimeters cubed is like how I find the volume of a cube. Length times width times height, right? So centimeters times centimeters times centimeters would give me centimeters cubed. Okay, so this conversion factor right here is one that is used a lot in medicine. Because have you heard when somebody says, I need 50 cc's of something,
Yes.
right? I watch a lot of Grey's Anatomy, so right, I'm basically a doctor at this point. But cc stands for cubic centimeters. So rather than saying I need 50 milliliters of something, or 50 cubic centimeters, they can say cc's, right? And that's really the only thing, the only place I see that come up. But this conversion factor, I would maybe highlight that or circle it or something in your notes, because it's one that we'll have to use semi-often. Okay. And when I say conversion factor, you're really not even having to do any math, because they're equal to one another, right? 1 milliliter is equal to a cubic centimeter. All right, we're going to talk now about taking correct measurements. Taking correct measurements. In every single measurement you take, there is what's called uncertainty. Okay, uncertainty in measurements. And that just means that unless we're using something digital, there's likely to be human error in our measurement. Would we agree? Mm-hmm. Right, there's just likely to be human error. And so there's some degree of uncertainty always. Here is the tagline that I give you when we take measurements. Okay, what we're going to do is record the certain digits and the first uncertain digit. Okay, and I'm gonna give that to you in non-textbook language. Okay, when we take a measurement, what we're going to do is read what the instrument gives us. So read what the instrument gives you and estimate one more digit. Okay, so you're going to read what the instrument gives you and estimate one additional digit. Okay, and we're going to just walk through several examples of what this looks like. Okay, read what the instrument gives you and estimate one additional digit. So that means not every measurement we take will be to the tens place or to the tenths place or to the hundredths place, or not every measurement we take will be the same, because every measurement instrument that you use, a ruler, a graduated cylinder, they're all marked differently. So we can't always say every measurement we take has to be to the hundredths place. We can't say that because we just don't know what all of our instruments are going to be measured to. Okay, so let's take a look at this right here. This is a volume example. Okay. Oops, sorry. This is a volume example. When we read volume this way, do you know what this little curved line is called? You know what that's called? The meniscus. Okay. And when we measure water like this, do you know, yes, near your knee also. Do you know why this happens with water? Water always forms a meniscus in glassware. Do you know why?
Viscosity.
Kind of, yeah, it does. It has to do with surface tension. So what it's going to do is climb up the sides of the wall, right? Because there's so much tension on the surface of the water that it wants to just connect with each other, and it'll just climb up the side of the glass, okay? And so it forms this curve. And when we measure water, we have to measure from the bottom of the meniscus. So when we see that curved line, we're always going to measure from the bottom of that line. And so our measurement right now gets taken from this place right here, okay? So I'm just going to keep it zoomed in. Okay. This measurement is taken somewhere between 20 and 19. Okay, we didn't pick a very good one here. Okay. Let's take a look at this glassware in particular. This glassware has 19 milliliters marked up here, then 20, then 21. Do we see the difference there? So that means this would be 20.1, 20.2, 20.3. Agreed? Okay. So in this particular example, I know the meniscus is between what and what?
20.1 and 20.2.
I know it's between 20.1 and 20.2. So these are the things I know. I know it's at least 20.1. So there's me reading what the instrument gives me. Okay, I'm reading that. Now I get to estimate, where does that line hit between 20.1 and 20.2? What do you think? 20.15. Anyone else think something different? Shout it out.
Why doesn't it like go the other way?
Why doesn't the go like, oh, you mean the glassware? Why is it counting downward?
Yeah.
Yeah, this is a weird example. Okay, this glassware is something called a burette. See how it's got this little tip at the end? So in this particular glassware, water like leaks out the bottom or drips out the bottom. And so in this glassware, you only measure by difference. So we know how much volume you start with and you know how much volume you end with, and then you subtract those things and it'll tell you how much liquid you dropped out. So we don't typically measure glassware upside down. So I didn't pick a very good example for the first one. Okay, or the textbook didn't use a very good picture on the first one. But typically our normal glassware is measured upward. So we'll be able to look at that. But yeah. In this example, if we was okay. In this example, if we started at 20.15 and we drained out all the water until we got to 24, we would say 24.00 minus 20.15, and that would tell us how many milliliters of whatever we used. Yeah. But anyway, okay, do we feel good about the guess right there, that estimate?
Yeah.
Okay. You get to choose. So that is literally just an estimated digit. Could I say it's 20.150?
It's the same thing.
Nope, it's not. That's a good question. Why is it not the same?
This would be like 100. It's a little less.
Okay. What I'm getting at is that if I put a 0 on the end, that would tell me that I knew it was exactly 5. If I knew it was at 1.5. And the 0 would be my estimate there. So if I add a 0, that's me saying that like my measurement tool was one more order of magnitude more exact than it actually is. Right? So it would be like me saying it's too precise and it's not. Okay. Good question though. Okay, let's look at the
And uncertain.
Okay, this is circling your certain digits and circling your
Okay.
uncertain digit.
Do you want us to write that on there?
You can if you want. Sure, you don't have to. I won't ever make you circle certain or uncertain,
Okay.
right? We just need to make sure that when we take the measurement, we do that estimation of our last digit.
Okay.
Okay, and no more than one, just one.
So it's always on like a line, like it was just there.
So this one was measured, example here. Okay, I think all these are in your notes. And so these are back to regular graduated cylinder types. Let's look at the first one. This is measured, here's a big tick mark at 20 and a big one at 30, which means what do those individual tick marks represent?
1.
They're single ones, okay? So that means we are at 21, 22, 23, 24, and 25. So what do we think about this one? Okay, so it's 24, and then do we just leave it at that?
We don't have a measurement.
We need to estimate another digit, don't we? Because we read it as exactly what it gives us, which is the ones place. So we have to estimate one more digit. So do we know it's greater than 24 but less than 25? Yeah? And do we think it's hitting exactly on that line? That's when we add a 0. Okay. But can I add multiple zeros?
No.
No.
So you always have to go to the tens place?
So I always have to go one more than what it gives me.
Because on this where it says certain digits and uncertain, you would write 24 on certain, and then uncertain would be 24.0.
Yes, exactly.
So on this, why does it say the same number for certain?
In this case, if it was like a 23, we just put 23.0.
Yeah, if it was right there, we'd put 23.0. Yep. To the ones place, which means that's why we went to the tenths place.
Okay.
Look at our next one here. Between 30 and 40, what do these tick marks represent? 32, 34, 36, 38, and 40. So this one isn't even really measured to the ones place. It's measured like every 2 milliliters. So what can we do here? What do we think?
38.
I think all we can do there is 38. I don't even think we can say 38.0 because there's a level of uncertainty even within our tick marks.
Because there's 2.
Because there's 2 milliliters between. Yep. Okay, then let's look at our last one here. This goes between 6 and 7. So what do we think? 6.60. Because the 6.6 here is known, And then we're going to add our last digit here, and we think it fits exactly on there. What do we think about that? Okay, so our rule is if it's measured to the tenths place, then we take it to the hundreds. Right? If it's measured to the ones, then we take it to the tenths. Very rarely are we going to see them like that, where they're every two, but it's good to practice. Let's try with a triple beam balance. How many of you have used a triple beam balance before? So based on this triple beam balance, I would say the mass is 434.12.
Oh my God.
1-1.
Yeah, 1-1 would have been fine. 1-1 would have been fine. Is that what you had?
Yes.
Okay, good. Okay, so not that. Let's say instead it is, I think you just get to go 0.2.
Just 2.
Yeah, I don't think you get to estimate after that. Maybe you do, I don't care. 0.22.